Thank you. I'm just trying to find my notes. There they are. Well, thanks again. Thanks for all showing up for part 2. Nothing I talked about in the last talk was mine, done by me. Everything I'm going to talk about now is joint work with Jason Manning. And I should say this is joint work in preparation. We don't yet have a preprint. We've done most of the technical details, so but anything I claim as a new theorem should have inverted commas around it for now. But we're pretty confident that none of the details left are going to cause any trouble. Okay, so let me just, I just erased the 2 theorems I said I was going to generalize, so let me just remind you what they are. So theorem of Y's says if G is hyperbolic, so hyperbolic is Gromov hyperbolic, but I'm just going to say hyperbolic now because we're amongst friends. G is an amalgam. There's an H and N version as well. C quasi-convex in G, and A and B virtually special. Then G is virtually special. So if you have the fundamental group of a special cube complex, then all of the hyperplanes are embedded, and you can cut along them. The hyperplanes are locally isometrically embedded, and so they're pi1. I mean the pi1 injective, and so you get a splitting either as an H and N extension or an amalgamated. If you have a special cube complex, and then you can keep cutting along the other hyperplanes, and eventually you'll cut it up until you have the trivial group. So every special group can be assembled via certain graphs of groups constructions into the final group. This is kind of going in reverse. This is saying if you have some algebraic structure where you can break things up in this way as graphs of groups, then in fact you're virtually special. So this is a huge deal harder than the theorem that says if then you can then you get the converse. This is so I refer to this as Wise's quasi-convex hierarchy theorem. I think that's pretty standard, and this is I think the major result in Wise's 100 and whatever page manuscript. There's plenty of other things in there as well, but this is sort of the major result. And then also, as I mentioned last time, Ian proved that if G is hyperbolic and G acts properly and cocompactly on a cat0 cube complex, then G is virtually special. By the way, it's not at all obvious that such a group should even be residually finite before Ian proved this, let alone that it has all of these other separability properties, that it's linear over Z, that it can be embedded in a RAG, and so on. All of these things are new for such a group. Before Ian's theorem, essentially, other than that this statement is true, nothing was known for this beyond what follows just from hyperbolic and cube complex. And the thing that needs to be proved for that theorem, you have a quotient cube complex or Orbi complex if there's torsion in G, and you need to be able to take the hyperplanes that are immersed and lift them to embedded hyperplanes, and then arrange the other pathologies to disappear as well. In fact, what Ian does is find a cover where the hyperplanes are all embedded and two-sided, and then apply this theorem because he already has a hierarchy. Okay. So those are sort of the 2 biggest, I think, results about these cat0 cube complexes that, I mean, and they've had, as I told you, spectacular applications. So I'm interested in a theorem that doesn't have such obvious applications that I hope there will be, but sort of is a simultaneous generalization of these. I will say we use both of these results in our proof. So it's not like I'm giving you anything new in this situation, but and I'll tell you in a minute what the, well, in a while, what the result that's generalizing these is. And I hope it'll have a number of applications. Okay. All right, so that's the two motivating statements. Let me remind you or tell you about certain other things that happen with hyperbolic groups acting on cube complexes. There's plenty of other interesting groups acting on cube complexes that aren't hyperbolic, but somehow when things are hyperbolic and have the cube complexes together, then sort of magic can happen. They play very nicely with each other, even though hyperbolic is coarse negative curvature and cat zero is honest non-positive curvature. In some sense, when you put them together, you get really a lot more information. The theme, everything today will be hyperbolic and be acting on cube complexes. So let me just remind you what Sageev was doing. I didn't say this in my previous part, but this is really what Sageev did. So H in G is codimension 1 if so take the Cayley graph of G and factor out by the H action. So this is Cayley graph of G. So this is either the covering of the rows corresponding to H or the Schreier-Coset graph or the quotient of the Cayley graph by H. However you want to think about it, it's all the same. This has more than one end. So this is more than one end. Okay, so from a codimension 1 subgroup, Sageev managed to find these partitions of the group that were equivariant with the group action, essentially from cosets of this subgroup that built a cube complex. You're looking worried, Ian, is it just?
No.
Okay.
If G is free product, then I guess.
That's, well, this is a definition.
Yeah, yeah.
I mean, I think.
No, that was just thinking about it.
Okay. All right. So Sageev says if G is a group, is a group, and we have some family of codimension 1 subgroups, then we get a cat zero cube complex X, say, along with the G action. Well, I mean, an example, if I take the fundamental group of a surface and I take, what would codimension 1 be? It should be something one-dimensional. Let's just take this here. So I want to take H to be Z, generated by the map from a circle in with this base point, and G to be this. What happens if I take, well, instead of taking the Cayley graph, I should take the hyperbolic plane, and I should factor it out by the action of the cyclic group. I get an annulus that has the core curve, the blue curve lifts, and then an infinite annulus that has two ends. Okay, so it's the sort of thing that happens if you have a nice, say, totally geodesically embedded codimension 1 submanifold and you lift to the universal cover, you get this picture. Okay, so it's sort of coming from this sort of picture of what happens in a codimension 1 situation in a nice geometric situation, and it's abstracting it into a group. Well, so this is one way to think about how you can see that it's codimension 1. It sort of is two directions to go away from the group at infinity, and seeing it in this covering of the surface / quotient of the universal cover is a good way, I think, to notice this. It's ruling out the notion that this be a one-sided curve. By the way, then it'll be one. So that's why we want our hyperplanes to be embedded and two-sided, is so that this sort of picture is what happens in this covering space. And then you cut along the curve and something happens. So that's sort of where the codimension 1 language is coming from. Okay? Okay, so we get a cube complex along with a G action. And this, I mean, you don't need to impose any conditions on the group or the subgroups except that they're codimension 1. And it's a cube complex and the group is acting by isometries. And it's non-trivial, that's right. There's no global fixed point for this action. That's right.
There's actually slightly stronger condition.
That's right.
Just on hyperplane taken off.
That's right. Yeah. Okay, so yeah, as Ian said, you can say a little bit more than just that there's an isometric action. But what you would really like in order to, I don't know, apply this theorem is to get a nice, proper, and co-compact action. Then, I mean, suppose that G is torsion-free, and it's acting freely and co-compactly, and it is the fundamental group of the quotient, and so naturally the topology and the algebra can be played off each other. So one would like conditions that ensure that you get a proper and co-compact action. And when I say virtually special for a group, I mean some finite index subgroup is the fundamental group of a special cube complex. And so the action on the universal cover is proper and co-compact. So here it's part of the hypotheses. Here it's not. There's a tree on which it acts. A tree is certainly a cat0 cube complex, but it's not acting properly on the tree unless A and B are finite. So this comes with a co-compact. The quotient is an edge. A co-compact action on a cube complex, but not a proper action on a cube complex. So one would like conditions that make the action on the cube complex proper and co-compact, and then the topology of the quotient and the algebra are linked. Okay, so one side of the story is not so difficult. This is another theorem of Sageev, and that's if G is hyperbolic and H1 through HK are codimension 1 and quasi-convex, then the cube complex X as constructed by Sageev is indeed G co-compact. Okay, so the co-compactness in this setting of hyperbolic groups, and not any codimension 1 subgroups, but codimension 1 subgroups that are quasi-convex, then the co-compactness comes to you for free. By the way, of course, this is a codimension 1 subgroup. What's the cube complex that we get? Well, you never get crossing hyperplanes, so there's never any squares. In fact, it's a one-dimensional cube complex. You get a tree. That tree is the dual tree to the lift of this to the universal cover. You get a pattern of blue lines in the disk, and the dual tree to that gives you the cube complex, and it's the Basset tree coming from Van Kampen's theorem when you cut along this curve and think about reassembling with two surfaces glued along a curve. So that is what Sageev will give you in this example, and it is indeed G co-compact. It's got an edge as a fundamental domain that you can just see here in the quotient surface. Okay, so co-compactness is easy to discover in this setting. There's other settings where it's very hard to ensure, but in this setting, hyperbolic groups and quasi-convex codimension 1 subgroups, the co-compactness doesn't come for free. Sageev worked to prove this, but it's known, and it's been known for a long time. So it's much easier to find co-compact actions than proper actions. Here, the action absolutely won't be proper, because if you have a simple closed curve that's essential that doesn't interact with this blue curve, it's going to stabilize the vertex of the tree splitting that comes from this side of the surface. So it's not proper. In order to make this surface group act properly on a cube complex, you need to cut it along a filling collection of curves, and then it'll act properly. So properness is harder to ensure. So for hyperbolic 3 manifolds, the properness came from the fact that Vlad and Jeremy could find so many surfaces not just one, but so many surfaces that went everywhere in the manifold that everything got cut up and the action was proper. And that was the non-trivial part of what Berger and Wise did, was assembled how many surfaces they had in order to take finitely many that happened to cut everything up to get not just a co-compact but a proper action. There are other times when properness is harder to ensure. Okay, so I wanted to talk about two theorems today. So the first theorem sort of comes to what happens if you do this construction. How nice can you talk about? How nice is this cube complex? And so on. So it's suppose that G is a hyperbolic group acting cocompactly on a cat0 cube complex. Okay. So that cocompact cube complex X may or may not have come from Sageev's construction. It may be given to you by some other construction, or it may have come from this construction. So then, first theorem says the following. The following are equivalent. Hyperplane stabilizers of the G action on X are quasiconvex. Okay, so that will happen in Sageev's construction. The hyperplane stabilizers are pretty much the HI, and so they are quasiconvex subgroups. So that's a condition that naturally arises in this setting. And the second condition that is equivalent is that cell stabilizers are quasiconvex. So cell stabilizers for the G action on X are quasiconvex. So why would you be interested in cell stabilizers? Well, you want to look at the quotient space X mod G. Okay? Now, X is not acting freely on G, so you can't expect that the fundamental group of X is equal to G. But in the appropriate category it is. And what's the category? The category is complexes of groups. Okay? You should label your quotient via cell stabilizers and maps between cell stabilizers corresponding to inclusions. This is exactly what you do with when you write this as a graph of groups. The quotient of the Basset tree is an edge, and you write A on one vertex and B on another and C on the edge in between, and you define the maps from C to A and B via some sort of lifting and inclusion process, and you get the notion of a graph of groups. Okay, it's the quotient of the action on the Basset tree is a graph. But in order to recover the group G as the fundamental group of that graph, you need to label it with the cell stabilizer information. Okay? So you do exactly the same thing with this quotient cube complex. Or, well, maybe a square is rotated by a quarter, and then in the quotient you don't see a cube. You see some orbifold cube. But suppose that it's acting so that if you fix a cube set-wise, you fix it point-wise, then this quotient is some cube complex. Its fundamental group has nothing to do with G on the face of it. I mean, this is simply connected, so it doesn't have fundamental group G until you label it with the information of cell stabilizers. And then, in the category of complexes of groups, then it has the right fundamental group. And so you can start linking the topology of the quotient to the algebra of the group action only when you remember the information about the cell stabilizers. So if Sageev gives you some quasiconvex, or rather if somebody gives you some quasiconvex codimension 1 subgroups of a hyperbolic group, and you give them to Sageev and he gives you a cube complex, you know for sure that they're G cocompact. And you know for sure that the hyperplane stabilizers, which are essentially the HI, are quasiconvex. the cell stabilizers, which are what you're going to use to understand G via this quotient, are also quasi-convex. And in fact, the converse is also true. If the cell stabilizers are quasi-convex, then the hyperplane stabilizers are quasi-convex too. So as far as I know, this hadn't been proved. I think that surprised us. It's a little tricky to prove it. Maybe I'll talk a little bit about the proof. But as far as I know, that's something. Sageev's construction is 20 years old, but I think this appears to be new. Sageev didn't know that this was true. So I'm going to take that as evidence that I get to write our names on this theorem. Let me just point out one corollary of this theorem. If G is hyperbolic, and some family HI are quasi-convex in codimension 1, and X is the associated cube complex, then X is delta hyperbolic for some delta. So G is delta prime hyperbolic. Its Cayley graph is coarsely negatively curved, but it's not acting properly and cocompactly on X, and so you don't get to assert immediately that X is coarsely negatively curved. In this circumstance here, there's a quasi-isometry from G to X that just comes from the orbit map because it's a proper and co-compact action. And so X is certainly delta hyperbolic in this setting. But in the setting where it's not a proper action, that's much less obvious. And it follows from 1 implies 2 here. So the two-line proof, and I'm happy to elaborate on this if people want, is X is quasi-isometric to the Cayley graph of G with cosets of the HI coned. So by that I mean inside of the Cayley graph of G, there's just a copy of H and all of its cosets. You just add a cone point for each such coset, and so you take every element of the group H and you join it to this coset H1 by an edge of length 1. So you take G, and then here's this H here. You just add an abstract cone point and you add edges of length 1 to every single one of the probably infinitely many copies of H. That gets you some graph, okay? And basically, it's not so hard to see that this is exactly the coarse geometry of X, okay? This is making all of the subgroups that are of cell stabilizers. Yeah. Not HI. Sorry, vertex stabilizers. All of the things that act fixing points in X, you fix a point in this Cayley graph by coning it to a point. I'm sorry, that's the whole point of this corollary, is that we know that these are quasi-convex. So you cone off all of the cell stabilizers because they're acting with a fixed point on X. You make them act with a fixed point on the Cayley graph by adding this magic cone vertex, and H will just fix this cone vertex and permute the edges adjacent to it. Okay, and about 3 minutes thought and sort of rewriting the usual Schwarz theorem about quasi-isometry tells you that this is true. I saw this first written down in a paper of Charney and Crisp, but it's not surprising or difficult. So the space X is quasi-isometric to the Cayley graph of G, where you cone off all of the cell stabilizers to points instead of being infinite. So that's a basic observation. And then Bowditch says that any hyperbolic group is weakly relatively hyperbolic with respect to any quasi-convex subgroups. Okay, I'm going to not write that out in any readable way. Basically, there's a theorem of Bowditch that says in exactly this circumstance, a hyperbolic group and some quasi-convex subgroups, this coned Kähler graph is delta hyperbolic. If you know about relative hyperbolicity, it's not what's normally called relatively hyperbolic. It's weakly relatively hyperbolic, but in particular, this coned Kähler graph is delta hyperbolic. So Bowditch says that this space here, once you know the cell stabilizers are quasi-convex, this weird coned Kähler graph is delta hyperbolic, whatever it is. But it's quasi-asymmetric to x. Okay, so this is I've made more of this proof than I should have done by, first of all, getting it wrong. But this is pretty elementary corollary of, well, it follows immediately from two known results. Once you know, so the hyperplane stabilizers are quasi-convex, you need to prove that the cell stabilizers are quasi-convex. And then you can apply these two theorems. Okay. So as far as I know, neither of these things, this theorem here or this corollary, neither of these things were previously known, which surprised me. But anyway, so I might, depending on time and my energy level, I might tell you a little bit about how these go. But I want to tell you about the promised common generalization of these two theorems. So let me state that, and then I'll tell you a little bit about how that's supposed to go. So theorem 2, again, joint work with Jason, says, okay, so I want you to close your eyes and imagine the theorem that immediately implies both of these theorems. Got it? Okay, that's the theorem I'm going to prove. Okay, so just by the time I finish writing this out, I'm sure you'll guess what the theorem is. So suppose G is hyperbolic. And okay, so here I have a cube complex and here I have a tree. So I'm going to act on a cube complex because trees are cat-zero cube complexes. So, and G acts, so cocompactly. In both those theorems, the action's cocompact on a cat-zero cube complex. Okay, but here the action is not proper and here the action is. So, but here the stabilizers are at least virtually special and quasi-convex. I didn't mention that A and B were quasi-convex, but they are. And here they're finite groups, which are virtually special and quasi-convex. So that's the theorem. If cell stabilizers for the G action are virtually special and quasi-convex in G, then G is itself virtually special. Okay, so this is sort of, so G is acting on a cube complex, but it's not acting properly and cocompactly. So there's no obvious candidate cube complex. Here in this theorem, there's a candidate cube complex where you want to show the quotient has a finite special cover. And here you know a lot about the pieces, but there's no candidate cube complex. So here, again, we're going to have to find a cube complex upon which G is acting properly and cocompactly, and then prove that the quotient has a finite special cover. So in some sense, the theorem is more like Wise's theorem, except that now we're allowing actions on trees rather than just trees, cube complexes in general. And so the sort of place this might be applicable is if you're trying to do Sageev's construction, and you can find some codimension 1 subgroups, but not enough to make a proper action. If you find some codimension 1 and quasi-convex subgroups, you get a G cocompact cat-zero cube complex. If you can somehow, well, then the cell stabilizers are quasi-convex. Okay, so then the hard work is going to be showing that the cell stabilizers are not just quasi-convex, but also virtually special. And then you get this about the whole group. And once G is virtually special, it's residually finite and linear over Z and has these nice separability properties, and you can do lots of nice things. So I'm going to tell you mostly about how one should prove this theorem, or how we prove this theorem, and not focus so much on applications, because this is a theorem. The applications are all so far just planned / imaginary. So, but I expect that this will have a number of applications in situations where one can find some but not quite enough quasi-convex subgroups.
You just have to show G is cubulated, right? That it acts properly and cocompactly on a cat-zero cube complex.
Sure.
And you can apply A instead.
Sure. Go on then.
No, I'm not saying that.
Yeah, that is something that you could do.
Right.
In fact, we're going to do the other thing, and that's the other thing we could do is show that it splits as a graph of groups where the subgroups are quasi-convex and virtually special, and apply Wise's theorem.
I see.
And that's what we're going to do instead. But we're going to do that using Ian's theorem, as you'll see in a minute, but not Ian's theorem applied to G, but Ian's theorem applied to some carefully chosen hyperbolic quotient of G. Okay, so that's what's going to happen. I don't see an obvious way of finding a cubulation of G just directly. The cell stabilizers, we don't know anything about them other than they're virtually special. So they have some abstract cubulation, but extending those to codimension 1 they have codimension 1 subgroups inside themselves, but codimension 1 inside some cell stabilizer is not at all codimension 1 inside G. So you have to find some strange way of extending codimension 1 subgroups of small groups to codimension 1 subgroups of the whole group. And I don't see any way of doing that directly. So I agree. If I could just find a cube complex upon which G acted properly and cocompactly, we could apply Ian's theorem and we'd be done. That's not quite how we're going to proceed. Okay, that'd be great. I don't know how to do that, but maybe you see. So.
May I interject a comment?
Absolutely.
Suppose you're Jeremy 10 years ago and you have a hyperbolic 3-manifold, and then you know that it contains a single, quasi-Fuchsian surface. Can you cubulate it?
Right.
That's a special
Well, you have to know that the pieces that are not seen by the quasi-Fuchsian surface are. You have to know something about those, maybe by induction. Yeah, so this, you're assuming here very strong control about the cell stabilizers, and the cell stabilizers, you don't get to know anything about the cell stabilizers from the action on the cube complex. They're not moving anything in an interesting way. So, in order to apply this theorem, you probably have to work pretty hard to see what it is that's not touched by your cubulation. So, in your example, suppose it's an embedded quasi-Fuchsian surface, and you cut along it. You have to know something about the pieces that you get from that, like that they're virtually special. Here, if it was immersed, well, the vertex stabilizers are even harder to see somehow. But yeah. Anyway. Okay, so let me start to try and tell you about how this is going to go. What are we going to do? Okay, so here's the basic theorem, the technical theorem that's going to be used to apply to prove this theorem. So yet again, this is joint with Jason, and it says the following. So under the hypotheses of theorem 2. If, let's say, Q sub sigma, as sigma ranges over the cells, the cell stabilizers, then there exists a quotient map lambda of the group G to G bar that satisfies certain properties. So one, G bar is hyperbolic. Two, lambda of Q sigma is finite for all sigma. Okay. Three, if I take the, so I have a cube complex X on which G is acting. So I'm going to take the quotient of that by the kernel of this quotient map to G bar. Okay, so that's something upon which G bar naturally acts. Okay, so this is, well, a cat zero cube complex. Yeah, that's all I need. Okay, so I'll tell you maybe a little later about the things that go into the proof of this theorem. So the quotient is hyperbolic. The image of all of the cell stabilizers in this quotient is finite, and the quotient of the cube complex by the kernel of the action is a cat zero cube complex. So I'll tell you a little bit about what goes into that later. But first let me see how to get from this theorem to the proof of theorem 2. Okay, so given this, let's say proof of theorem 2. Okay, so I have a cat zero cube complex X upon which G acts, and I have the quotient complex X mod G. That's a complex of groups. Okay, so you should think of that as just taking the topological quotient, assigning it some cell structure according to subdivisions of cubes, and then attaching to it cell stabilizer information, just in the way, so this is a complex of groups, just in the way that you do for graphs of groups with Basset theory. So an intermediate cover is, so between the universal cover and this quotient is the quotient of X by the kernel of lambda. Okay. So I'm just gonna think about this here. Okay. So I'm gonna call this Y, this thing here, Y. Okay, because I can. So here I have some covers. This is just equals. G bar is a quotient group. I'm just telling you that there is such a thing. Given that theorem, I'm explaining it, but I haven't told you how to find that theorem G bar. The one-line proof is you do some sort of relatively hyperbolic Dane surgery, height reduction according to malnormal cause of the family of cell stabilizers. So since you told me at T you read the proof of the virtual Harkin conjecture, it's elaborations on the sorts of things that happen in the appendix of that.
So you're cutting out some, you're getting a boundary out?
I'm considering G to be hyperbolic relative to certain subgroups of the cell stabilizers. I'm taking quotients by finite index subgroups of those. I'm reducing height of quasiconvex subgroups. I'm iterating until they become height 0, which is finite. And I'm keeping all of this information along the way. So I'll come back to that maybe a bit later.
Well, it's good to contemplate what happens when it's just a tree. So then the quotient will be a finite valence tree. And then
That's right. I was gonna give that example in a minute, but thank you. Yes, that is exactly the right example, and I'll tell you about that in just a minute.
Is kernel lambda gonna act properly on X?
Okay, so kernel lambda is not acting anywhere. Kernel lambda, no, probably not. For example, for every cell stabilizer, kernel lambda contains a finite index subgroup, right? Because the image in G bar is finite. So kernel lambda is not acting properly on X. But G bar acts on X mod kernel lambda. Okay, so there's a G bar action here on kernel lambda mod X, right? And it's just because it's a regular covering, so the quotient group acts by deck transformations. It's a regular covering because this is a kernel, so it's normal. Okay, so this is a hyperbolic group, and how does it act? Well, the cell stabilizers here are going to be the images of the cell stabilizers here, and they all have finite image. So this action is proper, since the lambda of Q sigma are finite. You don't look happy, Jeremy.
I'm just thinking about all this. It's not exactly my field, so I'm just trying to follow the Q. So we're sort of nearly killing these cell stabilizers.
That's right.
And we're kind of doing it kind of for the reason that you're saying, in order to get this cat zero cube complex on which this hyperbolic group acts properly and cocompactly.
That's right. So it's proper because I made all of the cell stabilizers finite in this quotient. And it's co-compact because the quotient's the same. So I can take y mod g bar. Those are just equal as spaces. They're not equal as complexes of groups.
Right.
The stabilizers here are images of stabilizers here. So if you like this sort of thing, there's a morphism in the category of complexes of groups. If you don't like this sort of thing, it's the same space, and all I'm doing is I'm relabeling the vertices. Okay, so as Ian said, this is easiest to think of in the case of a tree. So let me do this in the case of a tree. I want to keep all of that. I want to keep Jason. I want to keep the corollary. So we'll get rid of theorem 1. We'll throw under the bus the idea that I might tell you how theorem 1 goes. And let's do an example. So, example. Suppose G is an amalgam. So G acts on the Basset tree co-compactly. Actually, let's do an H&N extension, because then at least the quotient is not a tree. But I'm trying to find a quotient where there's a proper action. Okay, so we have the Basset tree T, and this lies above this graph, which has A labeled here and C labeled here, and this is T mod G. Okay, what I want to do is I want to take a normal subgroup of G that induces some sort of compatibility condition on this graph of groups. So G bar is going to equal A bar H&N C bar, where A bar is a finite quotient of A, C bar of C. But so I have two copies of C in A, one for one end of the edge and the other for the other end of the edge. Just like if I cut a surface along a non-separating curve, I end up with a surface with two boundary components, and I end up with two copies of that cyclic group that I'm identifying under this H&N extension. So I have to take a quotient, say, I mean, this is an excellent example to keep in mind. I have to take a quotient of this surface group that's finite, in which these two things map to isomorphic groups. So they have an isomorphic image under this quotient of A, and it should be finite. Okay, so it's not hard to do that in this example. In more general examples, it might be hard to arrange that the image of C on one side of this graph of groups and the image of C on the other side that have to be identical to make an H in an extension. They have the same isomorphic image, and so you can glue them together. Okay, and that's sort of hidden in an unstated part of this theorem, that sort of thing has to happen. Okay, it's hidden because I didn't cut along it. I just took a quotient where this is finite and this is finite, and then I cut along it, and I got the two finite things are the same because I cut along this finite thing. So that's sort of hidden in here, that kind of compatibility has to happen because I didn't think about cutting it. Okay, so that's what's going to happen. This here, so I'm going to have this quotient map from G to this amalgam G bar. Okay, so it's a general fact that if you have a group acting on a simply connected space, and you take the quotient of that space by elements that act with fixed points, then you get something simply connected. Okay, that's a general fact. It's due to Armstrong in this generality. You have to act maybe cellularly on a nice complex. So this turns out is a tree. What tree is it? It's the Basset tree for this splitting here. Okay, so this is the Basset tree for G bar. Okay, and then the quotient is labeled, it's the same quotient, but it's labeled A bar and C bar. If A bar and C bar are both finite, then upstairs you get a finite valence tree, which is exactly what Ian was saying. So now we have a group acting properly and cocompactly on this tree, and it's virtually a free group in this case. But and so so you have a tree. You take a quotient. In this case, we want to take a quotient that's generated by something in A bar. So normally generated by something in A bar, it's generated by elliptic elements. That's what gives you a simply connected space. Okay, a graph is cat zero exactly when it's simply connected. The links are all a collection of points, so you just need it to be simply connected. It's automatically non-positively curved, so it's simply connected, so it's a tree. And then you get this, and this is the quotient we're looking at. Over here, I told you that this is a cat zero cube complex. That's what happened in this theorem here. Okay, the sort of quotient that I'm going to build with G bar, it's going to be necessarily the case that this is simply connected. It's the same reason. The kernel of lambda is normally generated by things acting elliptically on X. So Y is automatically simply connected. The hard thing is to make it non-positively curved. I said you have to be non-positively curved and simply connected to be cat zero. The hard thing to ensure in this theorem is that this space here is non-positively curved. Okay, that's where there's a new ingredient in this proof. It's a little new. It's not so bad. This is standard, this is standard, this involves some extra work. Okay, so what's going on? I have a covering map here. If you squint and think hard, then this is the space, these are the same space with different labels, and this is the same cover. Moreover, the covers of this space that are intermediate to this are in one-to-one correspondence with the intermediate covers here. Okay, that's the second isomorphism theorem from group theory. The normal subgroups, or the subgroups of G containing this subgroup here are in one-to-one correspondence with the subgroups of this quotient group. Okay, so that's all that's going on here. Okay, so let's have a look at what we've got here. We have a proper and co-compact action of a hyperbolic group on a cat zero cube complex. Ian's theorem says that on this right-hand side of the diagram, there's a finite special cover. Okay? So Agol's theorem implies that y mod g bar has a finite special cover. But there's a corresponding cover x hat of g mod x mod g, sorry. Should keep that. Let's put that up here. So let me redraw my diagram with some extra objects in it. So I have x, and I have the kernel of lambda quotient of x, and that was y. And then I have x mod g, and I have y mod g bar. This is a homeomorphism on underlying spaces, and so is this. I'm just thinking them with different groups. And in here, I have maybe y hat. And so this y hat, this is the finite special cover. And over here, I have a corresponding cover x hat. And there's a map here that's a homeomorphism on underlying spaces. I'm just passing between a group and its quotient group and looking at covers that are intermediate to the x mod kernel lambda cover. And there's the one-to-one correspondence. And everything acts exactly as you would think it would from first year group theory or first course in group theory or elementary covering theory. The fact that we're in this weird category of complexes of groups actually doesn't make any difference to any of this. There is this one-to-one correspondence. Okay, so this is a special cube complex. G, there's a finite index subgroup of G corresponding to this, but it's not. This does not have that as its fundamental group. Okay, this is just right. So this it does have its as its fundamental group in the category of complexes of groups. Though.
Why is x hat a special?
Oh, because it's a purely topological condition, and all maps from left to right are homeomorphisms / cubical isometries on the level of the underlying space.
Right.
Okay,
Right.
so
Okay.
so these are the same space. They just have different group labelings, but they're the same space, and so it's definitely a special cube complex. Even if this were an Orbi complex, this is a cube complex, and it's special. Okay, so that's good. And moreover, because it's a finite cover, then there is G0 in G finite index, so that in the category of complexes of groups, I would write orbifold universal, orbifold fundamental group. Okay, so the fundamental group in the category of complexes of groups of x hat is G0. Spaces and groups are the same thing. But, okay, so there is a finite index subgroup which does act on x with quotient this x hat. That's all I'm saying if you don't want to think about the category of complexes of groups. There's a finite index subgroup G0. So this, i.e. x hat equals x mod G0. Okay, that's all I'm saying. Okay, we're not quite done, but we've only got 5 minutes left, so we better be close. Okay, so that's there, right? Oh, that's there. I'm running out of space. Well, I've got rid of that diagram. I've got a new copy of that diagram. Okay, so hyperplanes in x hat are two-sided and embedded. That's part of the condition of being virtually special, being special. Okay. Moreover, as complexes of groups, they are pi1 injective. If you don't know why that might be true, then you'll just have to believe me. It follows, essentially the hyperplanes come from a locally isometric embedding, and then in the cat0 world, that automatically gives you pi1 injectivity, and that remains true in the complex of groups world, where we have these infinite cell stabilizers. By theorem 1, so remember we assumed over here that cell stabilizers are quasi-convex, and theorem 1 said hyperplane stabilizers are quasi-convex. Okay, so I have these hyperplane stabilizers that are codimension 1 because they come from hyperplanes, and I cut along them and I get two pieces. And so the special technology just says those hyperplane stabilizers are codimension 1. They're embedded, so I can cut along them. I can apply Van Kampen's theorem in the category of complexes of groups. It's ordinary Van Kampen's theorem, but you have to say something about complexes of groups. And so I get a hierarchy. I can cut along all of the hyperplanes one after the other until I've cut up the whole space. When I'm left, I've just got these little neighborhoods of vertices. So I end up with vertex stabilizers. So cutting along hyperplanes, Van Kampen's theorem gives a hierarchy, over here maybe. So it gives a sequence of splittings of G and then of vertex groups, etc. So I take my cube complex, I cut along it, I cut along a hyperplane, I get a splitting of G because I just did a cutting in the category of complexes of groups. I get two pieces, they have some more hyperplanes and they're embedded, so I cut along them and I cut along them and I cut along them, etc. Ending with vertex stabilizers, which are virtually special by hypothesis. So then I use Wise's theorem time after time after time after time. I start with things that are virtually special. I glue them together along quasi-convex things because they're hyperplanes. I get something virtually special. I glue together, I get something virtually special, and so on. And so iteratively applying Wise, G0 is virtually special. And so G is, because G0 is a finite index subgroup. Okay, so I had better stop because I'm out of time. So thanks for coming.